Good morning. Happy New Year. Welcome to another year here at Brave ENM. It's my pleasure to start another land grant seminar series for 2025 spring semester. And we have plenty of opportunity here to host great people. At the beginning, I would like to welcome you. Maybe I can wait a little bit more to have more students coming in and more presenters, but let me give you a quick overview. Before that, I would like to maybe call on our dean to really say a few words in this new year and this great opportunity here to host a colleague like Dr. Cardenas.
Well, thank you, Dr. Ferrer. Good morning, colleagues, and our virtual audience. Great to see you all today. I know it's been a challenging past few days, but who better than this college to navigate some of these challenges and overcome them successfully. So we're really delighted to have Dr. Cardenas here to kick off our our spring 2025 land grant seminar series, the very first of the year for 2025. So Dr. Cardenas is a distinguished national speaker. He has chosen Prairie View A&M University as one of the first institutions for his lectures as part of the prestigious 2025 Geological Society of America Hydrogeology Division's Birdsall, Grice, and Lamoureux Lecture Award. Do you know all of that without looking at your notes?
I have to.
You have to.
Yeah.
Awesome.
You're excused, but I don't have an
Yes,
excuse.
that's true. Yes. So once again, it's an honor to have you and host you, and look forward to our interaction during the seminar and beyond. Thanks,
you,
Dr.
Dean.
Perez.
Thank you. And if I can get the microphone.
Oh, yes, sir.
It was a loan. Okay. Again, I'd like to give you a quick overview before I give the microphone and to our speaker today. I'd like to give you a quick overview of the 2024 seminar series. It was a very productive seminar series. We had about 27 speakers. You see the picture of them throughout the semester, 15 in the spring and 12 during the fall. You can see them from Prairie View, from USDA, from UT Arlington, from Augusta University to Sam Houston. So we were well represented across the board. So these are the number of attendees, both online and virtual, and in person. So as you know, we stream it live through Zoom, also via YouTube, and people like you who we are privileged to have them in person here. So we had about 350 about on average 50 attendee per seminar, and the statistics are brought to you by Dr. Ripendra Awal. He's our statistician and really data analytics for the seminar, and an important person for us. I guess, as I mentioned to you, we are still accepting presenters for the spring semester. As you can see, we are almost over halfway. We still need 6 presenters. If you have someone that you would like to nominate or approach, or yourself you would like to present, we welcome you. So Dr. Dean D'Souza introduced to us Dr. Mayani Cardenas, our speaker for today. I just want something that very important for our student to mention here about his citations. He's well cited for his work. As you can see, a very high H-index of 66 overall and 44 during the last 5 years, with more than, if I can see my statistics, 12,000 citations of his work. So this is very impressive, and we're very privileged to have someone with his caliber. With that, he's going to be talking to us about the hydrobiogeochemistry of terrestrial aquatic interfaces from pore and the groundwater pore size to the continental scale. With that, Dr. Cardenas, welcome.
Well, thank you for having me. Thanks to Dean D'Souza and Dr. Fares and Dr. Awal, Ripendra. It's been great. I'll be talking a little bit about the lecture series I'm part of. And I also want to acknowledge that this work is a synthesis and a result of a lot of collaboration. This is really work that goes back to my PhD in the early 2000s, all the way up to now. So this is a really, really broad synthesis. You're in for quite a fast ride. We're going to go through almost 10 to 20 papers, and I synthesize each paper almost by one slide, but hopefully you get the gist of why this topic is important.
Please keep in mind that our audiences are not geologists.
Yes. And let me turn this on. I think this is on. Nah, I don't think it's working.
Oh, it should.
It was working earlier. It's not now. And the keyboard is not working either. So,
Okay. He would go ahead, please.
okay, cool. And this is really for a broad audience. I'm a geologist by training. I'm in an earth science department, but this is important for any environmental scientist, anybody working in the natural world. So what are so-called terrestrial aquatic interfaces? This is a typical figure you would see in a textbook of what the landscape looks like, particularly for a hydrologist. You've got all these water bodies and, different mountains, forests, until the ocean. If you break this apart in 3D, make a cross section, what you see is, of course, there's groundwater. There's water beneath your feet. And if you look at the flow arrows here, the flow paths, such as what you see here, this one here, there's always connections. Some of these groundwaters, these arrows below ground, they come out to surface water. Some of it is actually the opposite, not so much here, but you can have, like here, surface water coming in to become groundwater in the subsurface. So there's always these connections, and this is what I mean by terrestrial aquatic. Aquatic meaning a surface water body, lake, ocean, river. Terrestrial part in this case is terrestrial groundwater, water underneath your feet in the aquifers. There's really a few questions we're going to address. What are the mechanics of this exchange? This exchange here. What are the biogeochemical functions of these exchanges? We're going to look at the time and spatial scales because they're relevant to the biogeochemistry. And ultimately, as a scientist, we want to understand how the world works. When you understand something, that means you can predict something, right? You can't possibly understand something if you can't even predict it. So we're trying to get to what we call predictive understanding. This is really the map for the talk. And this is, again, looking at these terrestrial aquatic interfaces at the watershed scale. You see the watershed here on the right. Actually, I have another pointer.
The physical one too.
Physical one.
Yeah,
If not, I have one that's actually a green laser that should work.
Speaker is prepared, so.
Yes.
Yeah, magic, so it's coming.
he's gonna do 70 of these, so he's prepared.
I think. Yes.
Nice.
Actually, this is missing a slide. I might skip back a little bit. This version is missing a slide. Before I get to my talk, I had a slide that talks about the Birdsall-Dries and Lamoureux lecture. So I am this year's Birdsall-Dries and Lamoureux lecturer. It's the GSA, Geological Society of America's Hydrogeology Division. So hydrogeology is my field. It's a fancy term for groundwater hydrology. And every year there's 2 hydrogeologists who are chosen to basically travel around the world and just lecture. And I'm one of those. The other one is from the National Groundwater Association. It's called the Darcy Lecture. Some of you who know about groundwater, you've heard of Darcy's Law.
Yep.
And the other one is the Birdsall-Dries Lecturer. It's called Birdsall-Dries and Lamoureux Lecture now because when I travel internationally, I'm the Lamoureux Lecturer. When I travel domestically, I'm the Birdsall-Dries Lecturer. So I'm doing 70 of these throughout the entire year in about a dozen countries. And I just finished 7 lectures in the Philippines. I kicked it off in the Philippines because that's where I'm from originally. I'm actually still jet lagged. So if I yawn, I'm not bored of my own talk. I'm just jet lagged. And this is the first one I'm doing in the US. So this is actually my kickoff for the US and the first one I'm doing in Texas. So most of February, I'm mostly in Texas. So I used to have a slide for that. I need to reinsert it. I don't know why it disappeared. Okay, so this is the map. You can see these are these exchanges where you have surface water going in, becoming groundwater, coming out again to become surface water. If you actually zoom into this watershed at this scale of a river and its floodplain, you even see these flow arrows where river water goes below ground, comes out again. And if you zoom in further, if you say go to the Brazos River, you'll see the Brazos riverbed is not flat. It has bars, it has ripples, it has dunes. Even at the scale of these, there's flow in and out. We're going to look at all these processes across all scales. That's why we even go to the scale of individual sand grains of pores. Okay, this is really the message of my talk, if you're not familiar with this. And a lot of the people here are probably engineers. How many are engineers here? So there's a lot of engineers. And if you learn engineering hydrology, you learn flow and transport in a river, it's a one-dimensional pipe. And things go downstream, but they're interconnected through a network. The point here is the stream is not a pipe, okay? Because there's water going in and out of the pipe. It's not a pipe with closed walls. It's a very, very incredibly leaky pipe. It's a pipe surrounded by a sponge, essentially, or connected to a sponge. So that's the main thing I want you to get out of my presentation. And we're going to look at this leaky pipe at this scale first, where you have these ripples or dunes in a riverbed, and there's turbulent flow on top of it. What that does is it causes water to flow in and out. And really the best way to illustrate that is this animation. So this is experiment done by one of my master students where water in this experimental channel that we have is flowing from left to right. And we've got a big riffle here. You can see the scale here, that's 0.5 meter. Again, the river is flowing from left to right, not very turbulent, very quiescent actually. And you're going to see dye that he's gonna tag and inject, and you're gonna see that dye go in and out. So he just released dye here, and you can see the dye flow down, and it's coming out there. And same thing here. This dye went in, it's coming out there. This happens in every river, okay? So there's always this connection. And this exchange, we actually call it hyporheic exchange, where river water comes in and comes out again. That's hyporheic exchange. And the zone that it defines, we call it the hyporheic zone. So that's the other concept or word I want you to get out of this presentation. Here's another example. These are smaller ripples, a few decimeters long. This one is actually more than 1 meter long. So this is tiny. And then again, you'll see dye of water go in and out. So you see it go in, go out. You all saw that, right? So again, this happens everywhere. So what I first did is I tried to understand the mechanics of this process. Why does this happen? Why does water go in and out? Well, to begin with, what causes water to flow from point A to point B?
Pressure.
Pressure, but it's not just pressure. Gravity,
Flow.
potential energy, those are all correct. But there's something more precise. Diffusion is part of it, but it's not just pressure or energy or potential energy, but the gradient in all of those. A gradient. There has to be a gradient in potential energy. If potential energy is the same everywhere, nothing is going to flow. If gravity is the same everywhere, nothing is going to flow. and pressure. There has to be a gradient. Yes, a differential, a derivative, right? So I modeled the flow in this river over this dune using computational fluid dynamics. And the color is, hopefully you're not colorblind, is dynamic pressure. So you can see it's red here, it's high, and it's blue there. So if there's differences in colors, there's a gradient. If there's a gradient, there must be flow, right? So what I then did is I coupled that to a groundwater flow model of the permeable sediment with a dune. Since it has high pressure here and low pressure there, that causes this flow through the pores of the permeable sand. So that's the first thing I studied for my PhD. I looked at the mechanics of this process. We've gotten more and more complicated. We can do 3D simulations now. We can run these on supercomputers and cover several kilometers of rivers doing this sort of simulation on large supercomputers, right? Not on your desktop or laptop.
And UT is
And we do have big supercomputers in Texas that the different Texas universities share, based at UT. We've done this for other features. In this case, you have a log that's in the river, and that log will cause pressure variations around it, and that will also cause this hyporheic exchange. These are, you can think of these as maybe like vegetation in a wetland, stems, same thing. When turbulent water flows around it, it causes this pressure distribution, high pressure, low pressure, high red, low blue. So that causes these hyporheic circulation too. Hyporheic flow, same thing with cobbles, and even cobbles that we try to bury, as long as it's sticking out, it will cause these pressure perturbations, it will cause this exchange. All this to say, any complex riverbed will have these pressure gradients, will cause flow. And what we did was, since these are hard to measure, those experiments are hard actually the videos that I showed, hard to plan, hard to execute, takes months, right? But once you know how to do these on a computer, you can do as many simulations as you want. So we call that sensitivity analysis. You can do sensitivity analysis, which is what I did early on, is just run multiple simulations. So each one of these symbols is one simulation. And for each of these simulations, I calculate the flux, how much water is moving in and out through the hyporheic zone. And I also calculate how long that water spends in the subsurface before it comes out again, or its residence time. And obviously, the higher the flux, the faster the flow, the less time you spend inside the hyporheic zone. Just like if if my speed driving from Austin to Prairie View was fast, it will take me less time. But I decided to be chill with my drive and took it slow. So they're inverse. But because you can do these multiple simulations, we were able to develop equations that allow you to predict what the hyporheic flux is. I'm not going to show that equation, but basically what you end up having to know is, first off, in order for hyporheic exchange to happen, you need to know how permeable the bed is. So you need the permeability or the grain size of the sediment. You need to know the shape of the roughness of the bed form. Is it flat? Is it long? Is it a tall bed form? And you need the channel velocity. For the engineers, basically, you need to know the Reynolds number of the flow. But once you know that, you can pretty much predict this. And that's what we first developed. We now have this function or ability to calculate this flow. So now let's talk about the time that water molecules spend in the subsurface going in and then coming out. So let's look at these particles. Let's just watch those as they go in and out. And now you realize, well, the red ones spent less time and the purple ones spent the longest time, and it went in deeper. So now the residence time becomes not just one time, but it becomes a distribution of times. So now we have what are called residence time distributions. And let's do this one digital experiment where a dye is going to be injected from the channel. It's going to go into the sediment and come out again. So this dye, since this is a computer experiment, you can actually monitor how much this dye comes out, right? If you give the dye a concentration of 1, ultimately what should come out should also have the concentration of 1. But at the start of the experiment, it won't be 1 because the dye is still coming in and then eventually coming out. So from that, we get what are so-called breakthrough curves. The amount of dye coming out. It starts off as, at the start of the experiment, the water that's coming out should be, oh, it's hard to go back, should be clear, right? But ultimately, the water that's coming out after a long time, it will have the color of the dye. So it will go from 0 to 1. We call that the breakthrough curve. And this is a so-called breakthrough curve, where over time, in this case, 4 days, this is the concentration of that dye coming out. The concentration should reach 1 ultimately, or the concentration of the water coming in. But if you look at this, after 4 days, it hasn't even reached 1. That's surprising, right? Water that went into this dune in the riverbed, after 4 days, not all of it has been flushed out. There's still some that's inside. So we call this the residence time distribution is really broad. Some water starts coming out, some water actually spends a longer time inside, below ground. And we do that for different shapes of bed forms, different asymmetry, and different grain sizes, really different dispersivity, the different level of diffusion or dispersion of the dye. And this, you can actually just analyze this. Really, if you take the derivative of this, you get what's called the residence time distribution. This is like the histogram. So for the students, you're familiar, if you take an exam, the exam scores follow a bell-shaped curve, right? A normal distribution. You can think of that as this distribution, but this is the population or frequency of molecules that spend this much time inside the hyporheic zone versus this much time. But notice this is logarithmic. And this is also the frequency, or PDF, is also logarithmic. Bell-shaped curve in this log-log situation will be actually a perfect U, inverted U. Well, this is not. This is anything but a perfect U. And this one is a straight line in a logarithmic plot, log-log plot. What does a straight line in a log-log plot mean? It's a power function. It's a power law. It's exponential. So that means the residence time distribution is a power law. It's not Gaussian. And power law, theoretically, because this is log-log, this would never go to 0 because it's logarithmic. So that means there's always some water that's spending, and notice this is long time. There's always some water spending a long amount of time in the subsurface. Theoretically, it never comes out. It's trapped.
Dead ends.
Yes. So these are called, they have long tails. These are power law residence time distributions, which is pretty unique. Why is this important? It turns out this is very important for chemistry because chemical reactions happen at different time scales. Some reactions are fast, some reactions are slow. But if you have this pocket of water, some of them spend a little bit of time in the subsurface and some of them spend a long time, that means collection of reactions are enabled or are allowed to happen. So some reactions that typically happen, one is respiration. So who likes to respire? Hopefully all of you like to respire, right? You're respiring your breakfast right now. You take carbon and you take O2, you produce CO2. And that all the bacteria in the riverbed respire. Okay, so this is respiration, breathing, essentially. Other reactions, and some of you I know since there's a lot of agricultural research here, so you're very familiar with nutrient cycling, particularly with nitrogen, right? Denitrification also happens when it's less aerobic. And then even ultimately, you get methanogenesis. But basically, you go from aerobic or oxic reactions to anaerobic or anoxic reactions because the oxygen gets consumed quickly. Okay, so now we're going to look at the chemistry of these processes. This is a pretty neat experiment. Again, we've got a small tank where we have ripples and water is flowing from left to right of this tank. So if water is flowing and you've got ripples, what do you expect to happen? There's a gradient, which means there should be hyporheic exchange. There should be hyporheic zones. Yes, because the gradients are present. We all agree now? It always happens. When there's water flowing over an irregular surface, there's going to be pressure gradients. And if the sediment is permeable, there's going to be hyporheic flow. Something that's really cool in this exercise is this is a homemade sensor where this yellow film actually quantifies or measures oxygen anywhere in that yellow film. You just take a picture with a camera like that, a nice SLR camera with the proper filters, and you can actually convert that picture into dissolved oxygen, which is what this is. So oxygen, it's oxic on top. That's the boundary of the ripple. And you can see oxygen is coming in because of the hyporheic exchange, but it disappears. It disappears because of microbes doing respiration. They're using the O2 because they like to live like you and me, right? And they're producing CO2 and water. So this is respiration in action, and we're able to capture that. And you can see as you get deeper, there's no more oxygen left. So here you would expect another reaction, right? Which would be an anaerobic reaction. And this is actually pretty cool. At the end of the experiment, we turned off the pump. When we turn off the pump, the river turns into a lake. It cuts off the circulation. So the flow that was delivering the oxygen doesn't exist anymore. So the oxygen that was left there was just used up. Which means if you're a microbe, you would not be very happy if you like oxygen after hyporheic exchange is cut off. Because you don't get the supply. You don't have the flow of water providing oxygen. The neat thing is, after we did these experiments, you can build computational models. So aside from the flow models that I told you about, we also do reactive transport models where we transport all these elements, the chemicals, the compounds, and they undergo all the reactions. So this is one such model actually for the whole experiment where you can see all the oxygen coming in is being used up from basically saturation to none, right? It becomes anoxic. So another way of saying we can do virtual experiments that represent reality well. And we like doing that because once you do that, like the experiment that I showed you is somebody's PhD. And they did maybe 3 experiments because it took forever to design the instrument and make it work. Once you have a model like this that's working, I can run thousands of these on a big computer. It's kind of heartbreaking for the PhD student who did the experiments, right? But that's the point of this study. We try to always connect experiments and models. Okay, so the next reaction then is denitrification, which will happen deeper where it is less aerobic or anoxic. This is a harder thing to measure. So what we did is we put a grid of gels in the walls of this experiment. And this gel allows the water to diffuse into the gel. And once the water is in the gel, we can analyze the gel. So this is that instrument here. And that's the result for nitrate. And here you can see nitrate is high. It's coming from the river. It goes in and then it disappears because the nitrate is getting denitrified. So this is denitrification in action, right? In denitrification, nitrate is denitrified. It will turn into
ammonia, nitrate. Okay, and then, yeah,
if it's complete, it will turn into N2O or N2.
get
Right.
nitrogen.
And we're able to model this too. So the model works well. This is a virtual experiment, but this is N2, which is really cool. We're also able to measure N2. And you can see this is the N2 produced from this denitrification. It's actually lower because the flow keeps on happening deeper and deeper. So whatever was produced in the shallow zone is pushed deeper, which is the N2. And this is, we can model the N2 too. And we're pretty sure this is denitrification and this is the nitrate we injected because we also isotopically labeled this nitrogen. So we can track it. And we know this N2 that's formed came from this nitrate. Okay, we'll look at other observations of this situation. This was work done by Amy Ford an undergrad in my lab, and Matt Kaufman, a former PhD student. I call it Texas size observations because we made this same gel that measures oxygen. It's the biggest one that existed at the time. There have been bigger ones, so I call it, that's Texas size. And this is what you're going to see here, dissolved oxygen here. But what we're going to do now is we're actually going to change the flow in the river. We're going to create a fake flood, have the river flow faster, and then decelerate it again. So if the river is flowing faster, what do you think will happen to the hyporheic exchange? More of it or less of it?
More of it.
More of it, right? And when we lower the velocity, it should become lower again. What should the oxygen do if you have more hyporheic exchange? It should increase, right? Because it's pumped in more. We'll see if you're all correct. I think it's playing now. Notice the time scale. Hours elapsed. So this is a long time. We just turn on the pump. So it pushed all the oxygen in. We're going to turn off the pump. And you can see it equilibrated again. So this just highlights how dynamic these systems are. We just turned the pump up a little bit and then lowered it. And what I want you to take out of this is, how many rivers have you seen that are at steady state? Even at base flow, rivers constantly are decreasing their flow. So that's just to say that, yeah, these things are very dynamic, and we have to consider how dynamic hyporheic exchange is. All the studies that I've been part of and others, they've kind of ignored how transient these systems are. We started with steady state models, for example.
It's difficult to model this way.
It takes more memory, for sure. But something that rivers always go through, and it will happen today and tomorrow especially. It was pretty cold this morning. It was really cold when I left Austin. And it was cold when I pumped gas into my car. I forgot how cold it is when I stepped out of my car. It was uncomfortable. But the temperature changes diurnally, right? It's warming up right now. It will hopefully reach 50 Fahrenheit, but it was close to freezing this morning. And when you have air doing that, what are the rivers doing? Same thing, right? So rivers have this natural diurnal cycle in temperature. They cool down during the evening and they warm up during the day. And this just shows actually the extent of that for many stations in the US. So one of my former PhD students analyzed this. This is the range for the day for different seasons. So you can see there are, like in the summer, you can get upwards of 6 degrees change in the river. In the winter, in this case, there's not much here, but even in the winter, we still get diurnal swings in Texas. So the question is, this is important for hyporheic exchange. I just showed you chemical reactions, right? And chemical reactions, almost all chemical reactions are temperature dependent. So first, let's look at how these signals propagate. Same experiment that I showed you before with the dye, but what we did is we put all these temperature probes in the same flume or tank experiment. It's actually covered by insulating material right now, so it doesn't lose heat. And what's cool about the experiment that we have is it has a heat exchanger and heater. It can actually warm up the water in the flume by up to 2 degrees per hour. So it uses a lot of energy, and it's very loud when you're there, when you're doing these experiments. It can heat it up and cool it down precisely, 1 to 2 degrees per hour, even if the water is flowing, which is what you're seeing now. The water's cooling down. You can see that cool water is coming in and then coming out here. Remember this hyporheic flow. And it's going to warm up, and you can see the hyporheic zone also warms up. What did it do? Yeah, you can see it warm up now. So basically, all these temperature changes in the river are also propagated into the hyporheic zone because of this hyporheic exchange. Because the water, of course, it brings all the chemicals, but it also brings heat. So there's heat transfer. So do these temperature changes affect the hyporheic zone? Of course it does, because this is what we know from textbooks, right? All the reaction rates and reaction constants you've learned when you're learning about chemical reactions, they're temperature dependent. Actually, we call that the Arrhenius equation, if you've heard about it, right? So this is just showing that where we run experiments at 5 degrees C, at 20 degrees C, and at 35 degrees C, and you can see how carbon is used up differently during respiration. This is dissolved oxygen. So when you're at a higher temperature, the DO doesn't penetrate much because it's used up faster, because it's warmer. And same thing with nitrate, right? Nitrate is denitrified sooner when it's hotter. And then ammonium is also being produced through ammonification. This is a bit of a complicated plot, but the one thing I want to show here is this is temperature corresponding to these experiments. So 5, 20, and 35 are here. This color tells you whether the hyporheic zone is actually a sink or source for carbon. It actually produces, nitrate. It actually produces nitrate through nitrification. So we have denitrification, but we also have nitrification, and they always happen together. Nitrification is oxidation, denitrification is reduction, but they're constantly happening together. So the question is, who wins? And this is what we see here. Just by flipping temperature, you can actually turn the hyporheic zone from a nitrogen source in blue to a nitrogen sink just by changing temperature, which is an interesting finding. We haven't done experiments to confirm this, but our models say so, just highlighting the point that, yeah, these are complicated systems. You have to think about the chemistry, but you have to think about the temperature too. And there's nonlinear dependency. We're going to zoom in and take a slight detour for a little bit and look at what's happening at the scale of pores. So these are now individual sand grains. And what you're seeing is flow through these inside those individual sand grains. And what we did was we ran some experiments where these spheres are sand grains. Okay? We model flow through the spaces between the sand grains. So this is actually the flow between the sand grains. So this sand grain is 2 millimeters wide. Okay? But we're modeling flow between two sand grains. What we then do is zooming in, we put in oxygen, nitrate, etc., and see where the denitrification happens. Is it happening inside the flow between the sand grains, on the sand grain? And what we also do is we allow the nitrate and all the other chemicals to diffuse into the sand grain, because the sand grains have porosity too. And that's what you're seeing here. So this is outside the sand grain, this is inside the sand grain. But what we found out here is denitrification is, in this very particular experiment, the denitrification is happening inside the sand grain. And the reason for that is there's no flow in the sand grain, but the chemicals are allowed to go in. So inside the sand grain, it's actually anoxic. And denitrification happens when it's anoxic. And we do two experiments. One where we consider the sand grain as totally impermeable, solid block. Nothing happens inside the sand grains. And another situation where we let reactions happen inside the sand grains. And that's what's being shown here. There's oxygen is going in, but it's being consumed inside the sand grain. And then that experiment, we take results of that and then do a larger modeling or computational experiment where we again have this ripple and let water go in and out and then calculate respiration and denitrification, in this case when there's no transport into the grains. And this is one where there's transport in the grains. So in this case, even the grains matter. There's a big difference. And the reason, the motivation for this is I had colleagues who were saying, my grains are so permeable, the sediment is so permeable, it should be oxic. There should not be any anoxic zones. But they kept on measuring denitrification in the lab. And it turns out because inside the sand grains, that's where the anoxic zones are. But they had very peculiar sand grains that were porous. They were actually, this is beach sand, and they were the sand was made up of corals. And corals are porous. So it's a very unique kind of situation. But in that case, what's happening at the pore scale matters.
It's not quartz sand, right?
No, not quartz sand. But you can have other forms of porous sand, but in this case, it was pretty unique. Okay, we're gonna zoom out to another scale where now you've got this river and water is going to go in and out of the side of the channel. So I'm gonna show you experiments again that prove this. This is at the University of Minnesota, the St. Anthony Falls lab, which, believe it or not, this lab is only 2 right turns from my office because it's along I-35. And my office is 1 right turn from I-35, so I can actually visit this lab with just 2 right turns. But I didn't drive, I flew, of course. But I found that kind of interesting because we're connected by I-35, right? The end of I-35, it goes south to Mexico, and then the end is basically the border of Minnesota. Okay, but they built this lab. It's called the Outdoor Stream Lab. It was a new facility at the time where they carved out a full-size river. It was a big empty lot. They bulldozed all the sand in it and then carved out a full-size river. They were actually trying to study the river. They're river geomorphologists, but when they did this, I told them, hey, I'm a groundwater hydrologist. Not only did you build a full-size experimental river, you just built me the largest experimental aquifer in the world. Because I view it as an aquifer, not as a river. So we went in there and put in these groundwater wells or piezometers to measure water levels inside the aquifer, right? And these are all the piezometers or wells that we installed, my 2 former master students. And from that, we can create a water table map. So these are water levels in the river and in the aquifer. And you can see water is flowing from left to right. So higher water level or head, lower water level or head. The river is going to flow down pressure or downhill. But because it's higher pressure here and lower pressure there, that actually causes this groundwater flow. So do you see these flow paths?
Mhm.
So it's this one here that I just showed you. Oops, sorry. I should put an arrow there just to make it clear. So there's hyporheic exchange again, but now at a larger scale. And what we did, so this is now all plan view of different rivers. These are not dunes, this is bird's eye view. And here you can see a river with low sinuosity, higher sinuosity, even higher sinuosity. So a big bend, and the river is flowing from left to right. But again, what that does is it causes river water to flow in and out, flow in and out. And I just do multiple experiments on a computer to do this, calculating how much water is going in and out, the exchange flux, running simulations with different valley slopes and river sinuosity. So this is sinuosity increasing from left to right. All these dots are the simulation results, and you can fit surface to that, an equation, which again allows me to calculate what is the area of this hyporheic zone and what is the flux through it, and therefore what is also the residence time of water in it. But we were able to develop this. I'm not going to show the equation, but we have a model to do that. One thing that's peculiar too is, where does water come from when it hasn't rained in a while and your rivers are still flowing?
Base flow
Base flow. What is base flow?
and the groundwater.
It's just groundwater coming in, right? If it hasn't rained in a while, rivers are still flowing. It's groundwater coming in. So we call that base flow. So what will happen if we actually have something like this? So this is the hyporheic zone. Water is flowing from left to right. But what if water is actually trying to get to the river? What will happen to this hyporheic zone?
Expand.
And let's say if all the groundwater is trying to get to the river, what will happen to this hyporheic exchange?
Increase, I mean.
Increase or decrease? They will compete, actually. So that's the hyporheic zone in red. But if you push water going to the river, this zone of exchange is diminished. Because remember, water has to go in first, but if this water is trying to go out of the aquifer into the river, this going in is harder. And in fact, the larger this increase, the smaller the hyporheic zone. And this is what's being shown here. This flux reduction, the flux decreases as you increase groundwater flow to the right. Until ultimately, you don't have hyporheic exchange because all the water is just going into the river. Okay, so groundwater flow is also important. These are field experiments that again show this is that hyporheic flow path. Water is infiltrating on this end, coming out here. This is dissolved organic carbon. This is dissolved oxygen. So notice the dissolved oxygen disappears, and so does the DOC. Because what's that process again? Respiration. So it's also respiration at this scale. And once all the DO is gone, what's the next process that happens? That's anoxic with nitrate, denitrification. And you can see the nitrate disappear later on. So again, you see this cascade of reactions happening now at a larger scale. And again, what allows this to happen is time, right? If respiration takes 10 hours and denitrification takes 30 hours, but if the water spends 50 hours, then both of them should happen. So this is now calculating, again, residence time from left to right. Blue is small residence time, and light blue is, I guess red is long residence time, blue is short. But going back to what I just said, what if a reaction takes an hour and the water is only able to spend half an hour? What's your guess of the extent of that reaction? Will it even happen?
It would be
But what
halfway.
would be, if you were going to bet, yeah, what would you say? Maybe half of it, right?
Mhm.
If it takes an hour and you only have half an hour, you might have half of it. But let's say you have 0.8 hours, what's going to be your guess?
Percentage of that.
Also 0.8, right? But what if, the reaction takes 1 hour, but the fluid spends 5 hours? All of it.
All of it, yes.
In fact, it might have happened fivefold, right? So we take the concept of that. Because we're able to calculate residence time, we now take the ratio of the residence time to the reaction time and calculate the probability of a reactant being used up based on this ratio. So you can see probability going from 0 to basically 100%, where carbon is used up 100% probabilistically by this end, nitrate by this end, and DO by that. For those of you who are familiar with transport, this is essentially a Dom-Kohler number. But we can do that now too, theoretically. That's the point. And now we're going to try and bring everything together at the largest scale, right? I talked about hyperic exchange at the scale of ripples, at the scale of pores, at the scale of floodplains. What happens at the continental scale? And we have issues at the continental scale, particularly with nitrogen. So this is nitrogen inputs throughout the Mississippi River Basin. And this is actually outputs. What that means is farmers are putting too much nitrogen. We're not optimized. We have excess nitrogen, and because of that, right, the nitrogen goes into the aquifer and goes into the rivers, the excess nitrogen. And all that makes it out where?
Yeah.
Gulf of Mexico,
Mexico.
right? Which is also why we have a dead zone in the Gulf of Mexico, because all those nutrients are used up and they use up oxygen in the process. So that's why we have dead zones. And this problem is continuous. This is a neat paper done by folks from Canada, by Nandita Basu, showing, yeah, this is a surplus nitrogen, and it's not, we've leveled, but it hasn't improved. And historically, it keeps on increasing. So the problem is going to be multiple generations, essentially, even after now. And dead zones are not unique to the Gulf of Mexico, to the Mississippi, right? We have dead zones everywhere because it's the same problem has happened in many parts of the world. So big question, really, right? Hyporheic zones, which are parts of rivers, denitrify. How come all that nitrate is not getting denitrified? So now we're going to try and address that, right? How much can be naturally denitrified in these hyporheic zones? But we're going to try and do it everywhere. So the goal really is to figure out the regional role of these hyporheic exchanges or river groundwater interactions or terrestrial aquatic exchanges in nutrient cycling. It's seldom done. We're going to try and do it. And we're going to apply all the models that we've developed and apply it across all scales. So I told you a few slides where we're not able to predict this. We're not able to predict that. We're going to use those equations now and apply it throughout the entire continent. Okay? But that requires a lot of data, putting the data together, and of course, coding, right? And it so happened, we had terrific people working on this problem and are able to put it together. So these are the hyporheic exchanges that I talked about when you've got riverbeds, small scale here, when you've got a meander, you've got this intermediate scale, but even when you have bars inside the channel, you've got hyporheic exchange. And I also told you if there's groundwater flow, it will compete with this hyporheic exchange. So you need to know that information too. And my actually academic sibling, my academic brother in grad school, put together all this theory. Because the question now is, how do you know what ripple you're going to have in this part of the Mississippi River? You don't. But river geomorphologists, people who study the shapes of rivers and riverbeds, they have theories for this. And a lot of them are hydraulic engineers too. So we just put those theories together where different meanders, bars, dunes, and ripples, you can predict them based on a collection of different input parameters. Now it's a matter of figuring out those input parameters, which are channel slope, river depth, bankful depth, grain size of the riverbed or the sediment, and bankful width. Some of these we're able to quantify using satellites. The rest we predict using theory. So first off, this is the first thing we compiled from EPA reports, printed reports. This was before AI will do this for you. You just download all the reports, put them on a map. So this is the median grain size of all riverbeds in the US. So D50 is what we call this in millimeters. And you can see some parts have coarse grained rivers, some parts have finer grained rivers in blue. So that's the first thing we needed to know. Next thing is sinuosity from a bird's eye view. How do you know how sinuous a river is? Well, you can use air photos to do that. So a former PhD student just downloaded air photos, wrote an algorithm that actually calculated sinuosity every 10 stream widths for the US. And that's what's being shown here in this map. Finally, groundwater flow. I told you groundwater flow can shut down a hyperexchange, but the USGS develops this product. They have this product that tells you the base flow index or the strength of groundwater flow into a given river section, which is neat. We have it everywhere and you can interpolate it. So from that, basically, we do some hocus pocus, run a lot of code, and now we can calculate the extent of two scales of exchange. Remember, I talked about two scales of exchange. Vertical, going inside the riverbed, and lateral on the sides because of bars and meanders. So first, let's look at this vertical exchange. Blue is high exchange, red is high exchange, blue is low exchange. And this is actually, it's log n, it's a number. It's actually the number of times a water molecule has entered the hyporheic zone in a given stream section, probabilistically. And you can see high rates in the headwaters, low in the middle here. And this is lateral exchange using the same scale. So if you look at this, what is more dominant? Vertical or lateral exchange?
Lateral, it looks like.
What's redder?
Oh, redder, yes.
It's
I mean,
actually negative
it's-
log,
it's-
so sorry.
okay,
Yeah. So vertical exchange is dominant. And this is something we didn't know what the result was going to be. But it turns out it's these vertical exchanges through the riverbed that matter more. The lateral exchanges are of a smaller magnitude.
It's the blue.
So next question. Okay, vertical exchange happens. In some places, not so much. In some places, it's pretty high. Next question, of course, is does denitrification happen in these zones where exchange happens? Right? And what do we need to know to figure out whether the reaction happens? Going back to some of the things I talked about, you need to know the residence time. So next thing we calculate now is the residence time of these exchanges. So first thing we learned is basically every water molecule that's going down the Mississippi River has entered the hyporheic zone at some point in its lifetime. Probabilistically, right? Not literally, but probabilistically, almost every water molecule has at some point entered into the riverbed or the banks and come out again. So this is the residence time for vertical exchange. This is the residence time for lateral exchange, just to show that we know that it happens everywhere. But there's a very important concept here, right? Because you can have, say, a water molecule, it might need an hour while it's underwater for the reaction to happen if the reaction happens it takes 1 hour. But it might only be spending half an hour. So maybe half of it might happen. But it might come out again, but it might enter again, right? And even if it spends another half hour, then those add up to like 100% almost. And if it does it multiple times, so odds are the nitrate in that water molecule can get reacted. So you need to bring two together, the number of exchanges and the reaction time. So we integrate those into a dimensionless number. Actually, this is just a good example of that. This is the denitrification time scale. And this is the cumulative distribution of residence time. So it's telling you these that are under this time scale, the reaction doesn't happen. Those that are above, the reaction happens. So it gives you a sense that a big part of the Mississippi River Basin is actually not denitrifying. It has a natural limit. But the reality is you need to combine the number of times it's entered the hyporheic zone and the reaction time. So I don't have time to explain this, but we calculated something that's called the reaction significance factor. It's essentially a dimensionless number that tells you if the reaction should have happened. If it's greater than 1, the log of it is greater than 0, the reaction completion is likely. If it's less than 1, then not. So this is or greater than 0 in log scale. So these are the good ones. Well, the reaction denitrification is likely, and these are the reaction completion is less likely. And you can see the deep reds, deep red here, some here, but even not a lot here. So it just tells you that the natural system has a limited capacity to denitrify. And we've put in a lot of nitrate. And where was if you remember that map from the USGS, where was the hotspot for nitrate inputs?
Midwest.
It's actually right here. Interestingly, where the hyporheic zone denitrification capacity is even lower. Actually, this is that slide. See, it's low here and it's kind of low there.
That's low. Okay.
And again, this is showing that a big percentage of all the parts of the Mississippi River Basin are actually not denitrifying to completion. So yes, the biogeochemical functions of the hyporheic zone have natural limits, is what we've established here theoretically. Another thing that we'll look at, let me just look at the time real quick, is I'm almost out of time, but is CO2. So remember, respiration produces CO2, but denitrification also produces CO2. And what this is showing is the percent of river water CO2 that was produced in the hyporheic zone. And you can see it could be a big chunk of it, 75%, some places 100%. So what this means is even carbon cycling in aquatic systems is strongly connected to these terrestrial aquatic exchanges, these hyporheic zones. And this is a big part of, this is the global carbon cycle, a report done by DOE. But freshwater outgassing from rivers or lakes has a unit of 1. If you actually look at it in terms of net carbon, it's higher than what forests do. Forests sequester a lot and release a lot, but they're close to balanced. But rivers, aquatic systems are net releasing. So this brings up like, oh, well, where does the CO2 come from? So now you think about, is the CO2 produced in the hyporheic zone? And that's what we tried to do. So we develop another model where we calculate respiration only using a theoretical model. We call it ARMS, aerobic respiration model for hyporheic zones, and applied it again for the entire United States. So this tells you the amount of CO2 respired from riverbeds. And I forget the big number now, but basically it's not trivial. It's dominant. It's the dominant source of CO2 on top of just background groundwater. So again, highlighting that these small things and exchanges, they really matter. They matter for the nitrogen cycle, they matter for the CO2 cycle. So to conclude, hopefully what you got out of this is this water exchanges or cycling across terrestrial aquatic interfaces. It's a natural feature of anywhere on Earth. These interactions are very sensitive to ambient groundwater flow. We show that. They take place across nested scales, from the smallest scales at the pore to scales of watersheds. These exchanges control biogeochemistry. We think we can predict them using theory. And really, when I ended with the last few slides, we think these are important for local to global biogeochemical cycles. So with that, very grateful to be here. Thankful for all the research support. And really, this was work done over many, many years by different people. Hopefully, it's not too much material for you guys and you got something out of it. Thank you very much.
Thank you. And, I think we can get a couple of questions for our speaker. You have any question for the speaker? Yes. Just a
Yes.
second, please. Let's for the online audience.
On the very last slide, you showed a map where there were more hotspots. On right side, left side, but
Uh-huh.
and you know what I mean? Why is it that there's more riverbed respiration?
Yes. I think those are, so I want to put a disclaimer first. We develop a lot of theory and these are a lot of theory for this and these are data driven. I like to tell people these models are wrong and right everywhere. Because, how are we to say that I can really go to this point and that's the number there? No, these are predictions. And we're dictated by the data too. And even the theory that we use has its own limitations. But they're going back to your question. The reason for that is these are mostly in the headwaters. So near where the watershed start, the river network start. And hyporheic exchanges tend to be stronger there. Water is flowing faster. The beds are more permeable. You've got cobbles and gravel, not just fine sand.
Another question. I'll get to you. Go ahead, please.
Thank you. So I know water resilience is a big deal in Texas right now. And, there are parts of like West Texas, I think that will, like the groundwater is, if I understand correctly, the groundwater is being used up. And I'm just trying to figure out how is that like nitrification and denitrification process going to be affected as the groundwater
Sure.
reduces?
So I think the bigger thing with that is one thing that's peculiar about Texas, right? And our water managers recognize this. Groundwater and surface water are legally managed separately because they're governed by different laws. I think as somebody who studies these connections, that's my biggest issue, is they're interconnected everywhere you go almost, but the laws don't recognize that. So that's I think the bigger issue. But going back to your question, I think what's happening in those situations, West Texas is unique though, because a lot of the rivers there actually dry up naturally. So they're called ephemeral rivers. Unlike say you go to eastern part here and further east to the bayou, really, the rivers are running year round. So there, I think the terrestrial aquatic connections are weak to begin with because the water tables are deep. So these sort of processes are less relevant there, except when we get flash floods and the arroyos have water. So these are the riverbeds that are generally dry, but when they get rainstorms, they run. That said, in places like Arizona, they've had rivers that were flowing year-round that are basically gone now because the water tables have dropped too deep. There's basically zero base flow, and they have that in places around Tucson, which means you lose these ecosystem functions.
One last question here.
Yeah, I have a question.
Yeah.
A comment, really.
Sure.
So I think one of the basic issues is that water is underpriced. If you ask an economist. So I think that is the source of a lot of the water shortages that we face, not just in the US, but globally. I mean, Mexico is pretty dry because the Constitution basically says that water should be zero cost to society. So I think the same in the US. So really it's, I believe the root cause may be economics more than anything else.
And I think what's changing in some fields, right, is these services that I told you, they're called ecosystem services, denitrification, is, and we try to denitrify in wetlands, and wastewater treatment plants are basically just denitrifiers to a certain extent, right? Any wastewater treatment plant has a denitrification step. But natural systems do that. But I think if we quantify the value of these ecosystem services, then that would, add another important dimension to what the dean said. It's not just the value of water per se, but the other services that the water provides, in this case, biogeochemical reactions.
Well, another question, I think we're going to have two more questions. I correct myself for not saying the last question.
Okay, good afternoon. This is just like not a supporting questions. Being a more nitrogen in the Mississippi River, do you think that means the farmers are applying more nitrogen or farmers losing more nitrogen? Because
I think it goes back to the economics. No farmer wants a loss, and fertilizers are cheap, and water is cheap. So if you can overwater, why not? If you can over-fertilize, why not? Because it assumes a good yield, right? It's hard to find that optimal balance, and it's pretty risky. You get a little bit of a drought, all of a sudden you have losses, right? And if you under-fertilize, it's a big problem.
No, but
So-
my question was that the farmers are applying the nitrogen
Mhm.
based on our recommendation, how much they require. But the challenge is they cannot control the river runoff with taking the nitrogen
Yeah.
before application
Right.
to the rivers. So that's a real cause, how to control the nitrogen, even we apply the right amount.
I see what you mean. Yeah, but so I think it goes back to the point. When you do that, then you have to look at the system more holistically hydrologically, right? Then you need to know how much groundwater flow is in your field, how much infiltration there is, and how much makes it out to your river, right? How much of the water and the fertilizer makes it past the root zone and eventually becomes base flow. But I think the issue with that now is, and the one paper that I mentioned, they've showed that, yeah, easily 50 years before you might even detect some change if we make management changes now. Because we've been doing this for a long time. And groundwater, I mentioned to you, these hyporheic zones have broad residence times. Regional groundwater has even broader residence times. So there's some groundwater that will take decades to come out. And if they have nitrogen, that's the nitrogen that will continually come out. There are management decisions we can do now. People are saying we can put more wetlands and optimize wetlands and riparian zones. That will solve some of the modern problem, but it's a decades-long problem that has a long history, a long memory.
Yeah, I think that's a key point here is like there is momentum for the things that we have been doing. So even if we stop now, it's going to take a while for the system to flash out. So so that means we have to look for long-term solutions to an environmental problem we're dealing with. So there is no magic wand that gonna help the question answer it right away. It takes some time. So with the last question here, so we're gonna end this, although the discussion is very, very important, and we don't have that someone with this caliber every week. So we would like to take one more question from here. So
Good afternoon. Thank you for the brilliant presentation. I just have a question regarding the methane interaction with these systems.
Methane?
Because you were mentioning some of the biochemistry of
Yes.
aerobics and anaerobics,
Uh-huh.
and that caught my attention.
Right.
I'm not in this field,
Sure.
an animal scientist, so I'm interested in everything related with
Mhm.
methane emissions. So could you please expand on that?
Yeah, so some people have begun to study methane. Because of the broad residence time of these exchanges, you can really get to really low, highly reducing environments where you can get methanogenesis. There's not a lot of research done, but I think there's fermentation that happens in these hyporheic zones. So there's probably methanogenesis, but that's something that I thought about getting into at some point. But yeah, hardly anything has been done. That's basically the honest answer. There's a few people who measure methane, but the issue with methane is once it gets into the river, it gets too toxic, it's hard to find it. But it might be getting produced in the subsurface.
thank you very much. Let's give
Thank you.
our speaker a round of
Thank you.
applause. And you know, he's not far away. He's only a couple of hours away from here. So hopefully this,
Shorter if you drive fast.
yeah. Residence time, right?
Yes.
So if you want to connect with him in the future, I think we're looking forward for that.